Computers excel at processing precise, tabular data. A programming language operates on strict rules of syntax. Missing a semicolon means the script fails. Human speech, on the other hand, is fluid, messy, and constantly evolving. It completely defies strict mathematical rules. The way we communicate is inherently ambiguous. The meaning of a single word fluctuates depending on who is speaking, when they say it, and the surrounding context. A single sentence carries overlapping layers of complexity. You have lexical ambiguity at the level of individual words, syntactic ambiguity in how those words are structured, and pragmatic ambiguity regarding the actual intent of the speaker. This creates a massive problem for computer science. A machine natively processes numbers. It cannot read a raw paragraph of text and extract meaning without a mathematical translator. This is the exact problem that natural language processing, or NLP, attempts to solve. NLP is a field of computer science aimed at mapping qualitative human language into quantitative, probabilistically predictable representations. To achieve this translation, engineers rely on a foundational architecture known as a language model. At its core, the operational goal of a statistical language model is straightforward. It looks at a given sequence of words and assigns a probability to predict the next word that will follow. Calculating that exact probability is difficult because human vocabulary allows for a virtually infinite number of word combinations. We cannot simply program a computer with thousands of grammatical rules and expect it to understand sarcasm or poetry. To make language computable, we have to build a system governed entirely by statistics. The theoretical starting point for predicting text is figuring out exactly how likely a specific sequence of words is to occur. We do this by calculating the joint probability of the entire sentence from start to finish. To find that joint probability, we apply the chain rule of probability to the sequence. Looking at this chain rule expression, you can see how the probability of a sequence of words, W1 through WL, is calculated. To evaluate a specific sentence, like "the cat sat on the mat," we take the probability of the word "the," multiply it by the probability of cat given "the," and multiply that by sat given "the cat." Predicting the final word requires us to calculate the conditional probability of every single word that came before it, combined. That works for a short sentence, but imagine expanding that historical sequence to a full paragraph or an entire document. The engineering reality is that processing true joint probability across large sets of text requires computing power that scales exponentially. Perfect linguistic prediction is mathematically unfeasible. To process language at scale, NLP engineers had to introduce a structural compromise to make the math tractable. That workaround is a principle known as the Markov assumption. This excerpt defines the Markov property. It states that the conditional probability of future states in a process depends only upon the present state, not on the entire sequence of events that preceded it. Applied to NLP, the Markov assumption means we estimate the probability of the next word by looking only at a finite window of previous words, completely ignoring the rest of the historical sequence. This assumption is the structural engine behind the n-gram architecture. An n-gram is the simplest statistical model used to assign probability distributions to text. The tightest window is the unigram model, where k equals 1. Here, the predictive window isolates individual words, completely disconnected from their surrounding context. To begin capturing local word order, the system expands to a bigram model, where k equals 2. The model now evaluates consecutive pairs of words. Expanding further, the trigram model evaluates 3-word sequences. This allows the system to capture slightly larger contextual dependencies as it slides across the text. We estimate these local probabilities using the maximum likelihood estimate. This means dividing the frequency count of a specific n-gram by the count of the historical words that immediately preceded it. By capping how far back the system looks, n-gram models trade long-distance grammatical memory for mathematical tractability. They make statistical language processing computationally possible. But this architecture has a severe vulnerability that reveals itself the moment an n-gram model is tested against real-world documents. The problem stems from out-of-vocabulary, or OOV words. Out-of-vocabulary words are valid terms that appear in the testing data, but were entirely absent from the model's original training corpus. The mathematical consequence here is immediate. If a word was never seen during training, its frequency count in the n-gram model is exactly 0. Because the chain rule multiplies all sequence probabilities together, a single term that drops to 0 acts as a mathematical kill switch. In a purely multiplicative probability system, the absolute certainty of a single 0 occurrence completely paralyzes the model's ability to predict the sequence. To prevent this probability collapse, engineers have to intervene mathematically. The first step is adding a special unknown token, often written with bracketed text, to the model's vocabulary to catch unrecognized terms. The primary method used to address this sparsity problem is a technique called Laplace smoothing. Laplace smoothing, also known as add-1 smoothing, works by initializing the count of every possible n-gram at 1 instead of 0. By artificially shifting the entire distribution of word counts up slightly, we guarantee that every sequence maintains a minute, non-zero probability. Laplace smoothing provides the mathematical safety net required for an n-gram model to process the infinite, unpredictable nature of actual human vocabulary. Once a language model is built and smoothed, we need a way to objectively measure its performance. We evaluate these models using a metric called perplexity. Perplexity is a measurement of how well a probability distribution predicts a sample of unseen text. Looking at the center equation here, perplexity is calculated as the inverse probability of the test sequence, normalized by the total number of words in that sequence. The scoring relationship is straightforward. Lower perplexity scores indicate a higher predictive accuracy from the language model. Minimizing perplexity is mathematically identical to maximizing the probability of the correct sequence. Figure 3.1 compares classical n-gram architectures against modern deep learning pipelines. These classical models were the critical stepping stone in the history of NLP. While modern deep learning utilizes neural networks to automate feature extraction and bypass manual n-gram counting entirely, it inherits this exact probabilistic objective. By accepting the Markov assumption to bypass computational limits, and by utilizing smoothing to handle infinite sparsity, classical statistical models laid the permanent foundation for how machines comprehend human thought.